So I was going to go over a couple of similar problems to homework problems because I think both of you actually had questions about kind of how to do problems 1 through 8. And I thought we should go over a couple, and then they're good examples. So let's look at question 3 from section 10.2, which is the following. We're given that A equals -1, -4, 1, -1, and we're asked to show that x1 of t equal to 1/2 e to the -3t plus e to the -t, and x2 of t equal to 1/2 -e to the -3t plus e to the -t. And that's just your symptom survey when you have a moment.
Oh, yeah.
We're asked to show that these are solutions to the system of equations dx dt equal to a times x. This pen is not living up to what I was thinking. So, thank you. So if we're doing that, what we're really just trying to show is we're trying to show that the vector dx dt, so x, I could write it as, I guess, dx1 dt, dx2 dt. I want to show that that's equal to this matrix times x1, x2. So what I'm really going to do is I'm just going to calculate both sides of this equation. So first, I'm going to show that I'm going to find dx1 dt, and I'm going to show that it's equal to -1 times x1 plus -4 times x2. I always get to do that. So that's what we're going to show first. So, okay, I know how to take the derivative of this. So dx1 dt is equal to, let's see, the derivative of this is going to be 1/2 times the derivative e to the -3t is e to the -3t times -3, and the derivative e to the -t is e to the -t times -1. And now I'm going to show that that's equal to -1 times x1 plus -4 times x2. So -1 times x1 plus -4 times x2 is going to be, well, I'm just going to throw those into it. So it's going to be -1/2 e to the -3t plus e to the -t minus 4 times 1/2 times -e to the -3t plus e to the -t. And then I'm going to simplify these both so I can kind of see what I'm looking for. dx1 dt here is equal to, let's see, -3/2 e to the -3t minus 1/2 e to the -t. Thanks. And if I simplify this one, so I'm going to get a -1/2 e to the -3t, and a -4 times 1/2 times -1 is a +2. And that looks worrying. It does look worrying. Have my numbers right? Have my matrix right? Have everything right? 1/2 e. That's all right. So we're going to do this and we're going to see where I went wrong. Minus a minus should be a plus, right? Yeah. 2 e to the -3t, and then I have a -1/2 e to the -t and a -2 e to the -t. That's worrying. These don't look the same. Meaning, right, if I look over here, I've got a -3/2 e to the -3t, and over here I've got a -1/2 plus 2 is a +3/2 e to the -3t. So I might have made a mistake. I've got a problem here too, right? I've got a -1/2 e to the -t minus 2 to the -t. That's the wrong thing. So let's check and see where I might have went wrong, right? Because these should be equal to each other if it's a solution. Right? Because it doesn't say like check to see if it is a solution. It says show it's a solution. So let's make sure I didn't do something dumb, which I did. and write down the wrong solutions to the equation. So I looked at the problem and I looked at the x1 and x2 that were above the matrix, not below the matrix. So I copied down the wrong solutions. So these aren't solutions to this. Apologies, I made a mistake. Sorry. So here's what the problem actually is asking us to do. So you could probably just totally forget about that. That was actually the solutions for problem 2. So here's what we actually wanted to do. So it is worth noticing though, right? Like if we were trying to show these for solutions, we're not getting there, right? Here we're getting a positive 3/2 e to the negative 3t, and here we're getting a minus 5/2 e to the negative t. Those are not the same. And the reason they're not the same is I wrote the wrong thing down. So we showed that they are not solutions to the system because I wrote down the wrong solution. So let's do it right. So here's what we actually wanted to do. We wanted to show that for the matrix, -1, -4, 1, -1, we want to show that these, okay, let's write them down the right time for real this time. x1 of t equal to e to the negative t times cosine of 2t, and x2 of t equal to e to the, 1/2 e to the negative t times sine of 2t. We want to show that these are solutions to dx dt equal to a times x. And the point of me going through this exercise to show you is that they're not asking you to solve the system, right? They're just asking you to show that the solution is a solution. So we're just going to show that x1 prime, x2 prime is equal to -1, -4, 1, -1 times x1, x2. Okay, this should work out this time. So x1 prime is the derivative of this with respect to t. Oh, I have to use the product rule. Interesting. So I'm going to get, let's see, negative e to the negative t times cosine of 2t plus e to the negative t times negative sine of 2t times 2, which we can probably simplify. It's negative e to the negative t cosine of 2t minus 2e to the negative t times sine of 2t. Right? Hopefully, when we do it the other way, it'll still work out. So this should equal -1 times x1 plus -4 times x2. Let's check and see. So if I do that, -1 times x1 is -1 times e to the negative t cosine of 2t, and -4 times x2 is -4 times 1/2 e to the negative t times sine of 2t. Yeah, that looks good. But that's going to be negative e to the negative t cosine of 2t minus 2 e to the negative t sine of 2t. And we can see that, yeah, these are equal to each other. So we've checked, well, we haven't fully checked, right? We checked that the x1 part works. We have to also check the x2 part works. So now we're going to check that x2 prime, which if I take the derivative of x2, it's going to be -1/2 e to the negative t times sine of 2t plus 1/2 times e to the negative t times the derivative of sine of 2t is negative cosine of 2t times 2. And then simplifying that, we're going to get -1/2 e to the negative t sine of 2t minus a 1 e to the negative t cosine of 2t. And then if we add 1x1 minus 1 times x2, we're going to get that minus that. So we're going to have e to the negative t cosine of 2t. I'm slightly worried. Minus x2, which is, yeah, Oh no, we're mostly good. Oh, no. Oh, I did make a mistake. I made a mistake when I took the derivative of sine of 2t. Right, this should have been a plus the sorry, pardon, where's my x2 here? Yeah, so I should have had, so there's your derivative of 1/2 e to the negative t times sine of 2t. And then there should have been a 1/2 e to the negative t times, oh yeah, sorry, there's my work right there. There shouldn't have been a negative sign right there. That's incorrect. So there should be a plus sign there. So that's a plus. And then, yeah, these are looking the same. They're written out of order, but they are the same each other. I've got a, sorry, yeah. I put the plus sign in the wrong place. Sorry, that's a minus sign still. I've got a e to the negative t cosine of 2t and a minus 1/2 e to the negative t sine of 2t. So they are the same if you're careful with your minus signs. So this type of problem isn't asking you to find the solution. They're just asking you to show that these derivatives are equal to these other things added together. That's it. You think I have a question? You're good. So here's my x2 and here's my x1. So to show that this was true, I was really trying to show that the derivative of x1, right, this component here is equal to that times that plus that times that. And that x2 prime or dx2 dt is equal to that times that plus that times that. I'm just doing the matrix multiplication. Cool. Okay. Let's look at one more just because the next one has a slightly extra piece we have to check as well. So let's look at the following one. This is 10.2 number 6. So now we want to do the same thing, show that x1 of t and x2 of t are solutions to the following. Well, to dx dt equal to a times x, where a is equal to the matrix -2, 1, -5, 4. And we also have the initial condition x not equal to 1, 5. We're given the solutions are supposed to be, let's make sure I get the right ones this time. x1 of t equal to e to the 3t. And x2 of t equal to 5e to the 3t. So the only thing additional that we have to do is actually really, really not terrible. Does this, so first, does this satisfy the initial condition? Well, yes, because x naught is just x at 0. So x naught is just each component evaluated at 0. But if you plug in 0 to the first one, you're going to get e to the 3 times 0. If you plug in 0 to the second one, you're going to get 5 times e to the 3 times 0. And that's exactly going to be 1, 5. So that worked out just fine. All right, so let's check. So, and again, right, we're checking really that dx1 dt, dx2 dt as a vector is equal to the matrix A times your solution x, which you could write as -2x1 plus x2 for the first component and -5x1 plus 4x2 for the second component. All right, and then we just do both sides of it. Now, really, you could kind of probably get it to be less because like they're going to be equal, but let's show it all out. So dx1 dt is equal to, well, that's not terrible at all. The derivative of this is just e to the 3t times 3. Whereas negative 2x1 plus x2 is equal to negative 2 times e to the 3t plus 1 times e times 5 e to the 3t. And negative 2 plus 5, that's a 1 times 5. Negative 2 plus 5 is 3 e to the 3t. So yeah, these are equal to each other. I want you all to check the next one. Check that dx2 dt is in fact equal to what? Negative 5 times x1 plus 4 times x2. There's x2. All right, so just to make sure everyone's cool with this, we took dx2 dt, we're going to get 5 e to the 3t times 3, which is going to be 15 e to the 3t. And then we're asking, is that equal to negative 5 times x1 plus 4 times x2? Well, negative 5 times x1 is negative 5 times e to the 3t. 4 times x2 is 4 times 5 e to the 3t. When we add those together, yeah, we get 15 e to the 3t. So we have verified that they're solutions. And that's all we have to do. We don't have to actually find the solutions because they were already given to us. Let's go ahead and, yeah. So let's look at another problem. Again, I will admit fully that this is not the part of this class I'm the best at, but I will still do it. So let's look at problem 10.2, number 13, where we are given the following. We're giving lambda 1 equals positive 2, lambda 2 equals negative 2. The eigenvector associated with lambda equal to 2 is 3, 1. And the eigenvector associated with lambda equal to negative 2 is 1, 1. We are being asked to sketch several solution curves in the phase plane of the system of differential equations using the given eigenvalues and eigenvectors. Okay, so we don't even get to draw the null lines here because we aren't given the differential equations. So you don't absolutely need the null lines, but we definitely do want the eigen lines. Now, before we even say any of this, we actually already know what kind of phase plane we're going to have. Since our eigenvalues have one positive and one negative, are we going to have a stable node, an unstable node, or a, what's the other one, a saddle? And we'll talk about that next. Okay, so let's take a look and then we'll talk. So here's what I would draw. In fact, this is where it's really, I'm also going to write the solution, the general solution, even though we don't really need it. So here's my general solution. And it's going to be that, x1 and x2 equals c1 e to the lambda 1 t times v1 plus C2 e to the lambda 2t times v2. Oh, that. I'm gonna do something clever. Maybe, we'll see. We'll see how clever I can be. Okay, so here is my phase plane. And on my phase plane, I really want to draw my eigen lines. So this eigen line is pretty easy to draw. It's along the vector 1, 1. So it's essentially the line y equals x, right? I'm thinking really what I'm thinking for this eigen line is I'm starting at the origin and I'm going over 1 and up 1. So my slope is 1. My line is y equals x. Over 1, up 1. So it's going to be the line that goes through these points. And it's just your good old friend, y equals x. I'm not going to draw any arrows at the ends. So this is the one that goes with lambda equal to -2. And then the other eigenline is over 3 and up 1. So over 1, 2, 3, up 1. So it's going to look like that. And I should have drawn them different colors, but I didn't because I forgot to. So there's my two eigenlines. And the thing you want to remember is that, well, in fact, let's actually talk about why this is true. So if I was on this eigenline, where my eigenvalue was negative, I would be heading towards the origin. Now you might wonder why that's true. And you'd be right to wonder why that's true. Well, let's take a look. Let me think about this for 1 second. That's fine, yeah. So if our initial condition is starting on the eigenline, let's say our initial condition is x not equal to 2, 2. We're starting at this point right here. I'm drawing in red. How do I know I'm going in that way and not out that way or some other direction? Well, let's actually solve for the constants here. Well, yeah, so the reason, definitely the reason we're going to kind of just say generally is, yeah, when the eigenvalue is negative, you're going to go inward. You're going to go towards your origin. But why? Well, if we actually solve for our constants here, look what happens. If I set 2, 2 equal to C1 e to the 2t times 3, 1. Oh, sorry, e to the 0 times 3, 1 plus C2 e to the -2 times 0 times 1, 1. I should have just skipped ahead and said that's going to give me 2, 2 equal to C1 times 3, 1 plus C2 times 1, 1. And you know what the solution to this is going to be? It's going to end up being C2 equal to 2 and C1 equal to 0. We could do the work, right? You could totally say 3C1 plus C2 equals 2 and 1C1 plus 1C2 equals 2. And then you could subtract them and you get 2C1 equals 0. So C1 equals 0 and then C2 has to be 2. But basically, the idea is that if your initial condition is starting on your eigenline, then that eigenvector is the only thing that's contributing. So starting here, our particular solution is that x1, x2 equals 2e to the -2t times 1, 1. That's our particular solution if we start right there. But now look what happens. This is a negative exponent. What's going to happen as t goes to infinity here? Right. As t goes to infinity, e to the -2t goes to 0. So this whole thing is going to go to 0 times 1, 1. It's going to go exactly straight towards the origin. And that's why in general, if you start on an eigenline, you just go in that direction, because what we're saying here, like if you kept plugging in different values of t, you would just get different multiples of 1, 1. So I know it's kind of weird, but like if I plugged in the value of t like 10, I would get e to the -20 times 1, 1. So my coordinate would be like a really small number, but I'm still on the eigenline, right? So if you start on an eigenline, you're just going on the eigenline. And if your eigenvalue was positive, instead of, right, so for example, if instead we started over here at the point 3, 1, then we would be going outward instead because our eigenvalues are positive. And you can do the same sort of work, right? In fact, we might as well, it's worthwhile. So if we started at the point 3, 1, I'm just going to tell you our particular solution would be, well, we're just going to get rid of the second part, and it's going to be x1, x2 equal to 1 times e to the 2t times 3, 1. Right, if I plug in 0 for t, I'm going to get 3, 1, which is my starting point, plus none of the rest. So I'm starting here, and then as time gets bigger, this number gets bigger, so I'm going out that way. And if I started over here, I would go out that way. So yes, if your eigenvalue is positive, you're moving away from the origin. If your eigenvalue is negative, you're moving in towards the origin. So interestingly, this system technically has one line of stability. It is stable along this eigenline. But if you start anywhere else, you're going to be unstable. So if you started like somewhere like, say, at the point 1, 4, we don't have the system of differential equations. We could try and solve for C1 and C2, but we don't really need to. What's going to happen is you're going to move kind of that way, kind of that way. You're going to go something like that. You're eventually going to get closer and closer to the one that has the positive eigenvalue because it's the one that's dominating, right? This term here, this part here is going to get smaller and smaller and smaller. This part here is going to get larger and larger and larger. So you essentially have something times the vector 3, 1 plus nothing or almost nothing. So we're going to move that way. Or you could start, I'm always like, this is the part where I'm like, I struggle a little here. I'm not gonna lie. You start something like here at the point, I don't know, 3, -2, you would move kind of in this direction. It doesn't have to be perfect. Also, if you wanted to really, well, actually you could. I was gonna say, if you wanted to check, you could graph it on a phase plane plotter, but we can't because we don't have the differential equations to start with. So this is all we can do. Questions about anything I've said? Yeah, Parville. I was avoiding that because it's the hard part. It's not impossible to draw. It's less good. So it gets kind of like, it's kind of extra wild. So if we start here, it's going to kind of go this way and then like turn around like that. So the only way you get right to the origin is if you happen to be on the eigenline with the negative eigenvalue. Otherwise, eventually, this stronger eigenvector is going to take over and push you way far away, either that way, or if you started here, like that. It's kind of neat. Yeah.
Makes the eigenvector like turns it 1 into a negative or a positive 2, like because you had 2 and -2, and now it's just 2 and 2.
Sorry.
So where it says if x is equal to 0 and then 2 and 2, I thought the eigenvectors were 2.
Right. So that's not the eigenvector. This is the initial condition. So if we're starting at the point 2, 2, then we're going to end up having our particular solution at that point is only this. And so I'm not saying, so the general solution is still this with both of the regular eigenvectors. But if we happen to start at a point that's on one of the eigenvectors, then the particular solution just becomes a multiple of that one eigenvector, which is the rationale for why we just end up going in that direction. The same deal is here. If I started an initial condition where I'm on that eigenvector, my particular solution is just a multiple of that eigenvector. So I end up going in that direction. You guys are asking good questions. You're welcome to ask others. So let's talk about classifying stability because it's definitely something that we care about in this class. And I'm going to draw some pictures. But let's actually start with this. So once again, the general solution to the equation, the derivative of your x1 and x2 equal to the matrix A times your x is going to be given by what we just talked about. X of t, or if you prefer, you can write it as a vector, x1 of t, x2 of t is equal to c1e to the lambda 1t times the vector v1 plus c2e to the lambda 2t times the vector v2. And we're going to reference this a few times when we talk about classifying solutions. So one possibility, both lambda 1 and lambda 2 are positive. Basically, what we're going to say is the system is stable if as time goes on, your x1 and x2 both get closer and closer and closer to the equilibrium, which is 0, 0. Right? So actually, I should ask you, does anyone want me to? I'm just going to say it. Let's go. I'm going to go real quick. Don't worry, we'll come right back. If this is your system of equations, dx1 dt equal to, I don't care, 4x minus 5y, dx2 dt equal to 3x plus 2y, the only equilibrium of a homogeneous, autonomous, linear system of differential equations is, I used x's and y's and x1s and x2s. Sorry, that's mean x1 and x2, x1 and x2. Sorry about that. The only equilibrium is x1, comma, y, x2, holy smokes, equal to 0, 0. This is the only place where nothing is changing, where both derivatives are equal to 0. Which makes sense because both of these are just straight lines and they're both going to cross at the origin. So the only place where they're both equal to 0 is at the origin. Questions about that? Yeah. Say that one more time.
Does that apply to every?
No. Eventually, well, probably not. I would imagine I think in section 10.4, 10.5, we do talk about nonlinear systems of differential equations, where you do have multiple equilibria on your face plane. And it's certainly more interesting. But these ones, I mean, they're good, but they do get kind of boring after a while. So not that there's nothing wrong with boring. Boring's fine, especially when it comes to math. You don't need to be exciting. You want it to be like understandable. But yeah, for now, if your system of differential equations can be written in this way, where it's, your derivative is a multiple of your first variable plus a multiple of your second variable, and your other derivative is a multiple of your first variable plus a multiple of your second variable. It's written in this standard way, or you can say in this standard way, then that means 0, 0 is the only equilibrium. Okay, so then if we're talking about stability versus instability, we're just asking, is it stable? Do the things get closer and closer to the equilibrium as time goes on? Or is it unstable? Do the things get further away from the equilibrium as time goes on? Those are the only questions we can really, well, those are the only things we're really saying when we talk about stability versus instability. And so if both lambda 1 and lambda 2 are greater than 0, well, look what's going to happen. Both x1 and x2 are going to get larger and larger and larger, because as time goes on, these things both get larger and larger and larger. So as time goes on and on and on, these two things, e to the lambda 1t times v1 and e to the lambda 2t times v2, well, both this and this both go off to infinity, because lambda 1 and lambda 2 are both positive. Graphically, like if you're trying to graph the phase plane, if this was your eigenline for lambda 1, and this was your eigenline for lambda 2, we would imagine, well, if you start like somewhere like here, you're going to end up shooting outwards. or somewhere like here, you're going to shoot outwards, right? There's a bunch of shooting outwards because your eigen lines are both pointing outward. So this is unstable, I should say. So we call this an unstable node. Some people also call it a source. And I would point out that we know a couple things about the matrix. We know that the trace of this matrix, which is equal to the sum of the eigenvalues, the trace is positive. We also know that the determinant, which is the product of the eigenvalues, is positive. Okay, so that's one thing that can happen. They can both be positive. They can also both be negative. So if both lambda 1 and lambda 2 are less than 0, well, then we can see that as t goes to infinity, our c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2, the e to the lambda 1 t part is going to go to 0 because our lambda 1 is negative. And the e to the lambda 2 t part is going to go to 0 because our lambda 2 is negative. So this is going to go to 0, 0. Meaning we have stability. So we have a stable node, also called a sink. Right? Think about a sink, like everything's draining into the sink. Right? We're going inward. Whereas a source, everything is emanating from the source outward. This would look similar-ish. We have, again, eigenlines that go through the origin, as they should. Now, along the eigenline, everything is pointing inward. Can I draw any arrows? Maybe. And so we're going, like we start here, I'm going to go like that. Like that. Now, if you plot these on something like p-plane, you'll kind of see, it's not, oh, sorry, if you'd like to see what I'm drawing, maybe, it's not always super like straight. Sometimes there's like a very kind of like curvy path to get there, but not a spiral. So sometimes you might start something more like, I don't know, you might end up with something like, maybe I ended up going like that for some reason. Maybe I went outward a little first for some good reason. But eventually you're always just pointing inward. You're not like going around and around and around and around and around. What else do I want to say about this? Oh, I'm also going to make some observations. So the trace here would definitely be positive or negative. What do you guys think? If lambda 1 and lambda 2 are both negative and we add them together, negative. But the determinant, which is lambda 1 times lambda 2, is still positive. Okay. And then we have the case where one of them is positive, one is negative. So it doesn't matter which one we say. Let's say lambda 1 is positive and lambda 2 is negative. So then in this case, we can see that as t goes to infinity, our c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2, the e to the lambda 1t part is going to go to infinity, and the e to the lambda 2t part is going to go to 0. So what's kind of interesting, this one still things are going to get infinitely large, but they're specifically going to veer towards your first eigenvector, or whichever one's associated with the positive eigenvalue. just like in the previous example we did, right? In the saddle we looked at before, all of our lines were getting closer and closer and closer to the eigenvalue, the eigenline associated with the positive eigenvalue. And that's always the case with the saddle. Is the one that's positive is the one that dominates. So here, you'd have something like, if I started here, I'm going to end up going like that. Or if I started here, I would end up like that. Saddle. So this is a saddle. And notably, the determinant here, which is lambda1 times lambda2, is negative. The trace, we don't actually know. The trace could be positive or negative. It doesn't actually matter. And then he did mention in last class some, he also mentioned if you had imaginary eigenvalues. So it's actually, the nice thing about imaginary things is it's kind of the same conditions as what we've already talked about. So basically, if your eigenvalue is positive, you're going to get this thing getting bigger, bigger, bigger. If your eigenvalue is negative, it's going to get smaller, 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 close to 0. But I know that complex numbers aren't technically positive or negative, right? There's this whole other imaginary part, which isn't a positive or a negative number. So let's look at that for a second. So let's say we have lambda1 equal to a plus bi. And the nice thing about imaginary eigenvalues is they do always come in complex conjugate pairs, meaning the real part is always the same for both of them, and the imaginary parts are opposite signs. So an example would be something like -3 plus or minus 2i. Those could be your eigenvalues. So we're going to have a similar condition. Oh, there's one other thing. There's one other thing I need to say. So when you're doing your solution, which is C1e to the lambda1, so that's a plus bi times t times v1 plus C2e to the a minus bi times t times v2. There's this whole kind of equation that's kind of wonky, which is that e to the I times, well, in this case, times bt, that's equal to cosine of bt plus I times sine of bt. It's a very famous equation. It's called Euler's identity or Euler's formula. I forget what it's called exactly. We can certainly talk about where it comes from if you want to. It's not super vital to be aware of, but if we're going to talk, let's save it for next. If you want to talk about it, we can talk about it on Friday. For now, let's just pretend like we believe that it's true. So it's true that e to the I times something is cosine of the thing plus I sine of the thing. People often write e to the I theta because you're taking cosine of the angle and sine of the angle. But the point is that this boils down to C1, I'm going to have e to the AT times e to the BI times t times V1 plus C2 e to the AT times e to the negative BI times t times V2. And then if you really, really want, you're going to get C1 e to the AT times cosine of BI, sorry, BT, apologies. Again, yeah, plus I sine of BT. V1, I know it's gross, plus C2 e to the AT times cosine of negative BT plus I sine of negative BT. V2. Okay. The good news is I don't think he's actually going to make you like do any of these ones where you have to find the eigenvectors when they're imaginary. It's really kind of a terrible process. But the point I want to point out is that, okay, if your real part of your eigenvalue is positive, look what's going to happen. If A is positive, this thing is going to grow and grow and grow. And so what's going to happen is this whole expression, both this part and that part, are going to get larger and larger and larger. But what's going to happen is the cosine plus I sine bt thing is going to make it oscillate, right? Cosine goes up and down, sine goes up and down. So what's going to happen to our solutions is like both x of t and y of t. In fact, I've got a picture over here that instead of me trying to draw something nice, let me just show you this picture I have. Yeah, not that one. Ah, come on. So what's going to happen is, so it's kind of dark right now, both x and y are going to oscillate, but they're going to get larger and larger and larger as time goes on because of that e to the at that's growing and growing and growing. So what we're going to see is both x and y getting larger, but kind of bouncing back and forth between positive and negative possibly. So we're going to get instability. And specifically, it's going to be an unstable spiral. So what's going to happen is we're not going to draw the eigenvectors because they're wonky, right? We're still, right, we're in the xy plane, but the eigenvectors are imaginary. We can't really draw them. But what happens is you've essentially got this spiral that's going out further and further and further. And if you think about this, the x and y values are both getting larger and larger. It's just like, so like over here, right, x and y are both really positive. Over here, they're both really negative. Over here, x is really positive, y is really negative. But they're definitely getting larger and larger and larger. Okay, one thing I want you to see here is that, so the nice thing here is that the thing about the trace is still true, meaning the trace, which is lambda 1 plus lambda 2, is a plus bi plus a minus bi, which is going to be a squared plus b squared. That might look funky to you. Let me write it out. It's going to be a squared plus a times bi minus a times bi plus, sorry, minus b squared I squared. The ABI's cancel. And I squared is equal to -1. That's the definition of the imaginary constant I. So this is going to equal negative b squared times -1, which is plus b squared. And that's definitely, wow, sorry, wow, you guys should have said something. I got carried away. What did I do with it? So I did calculate something that we also need to know. But what did I actually calculate? I didn't add them. I multiplied them. That's okay. That's the determinant. So the determinant is a squared plus b squared. The trace, sorry, is a plus bi plus a minus bi, which is just 2a. So the trace is positive, and the determinant is also positive. Kind of neat. I wish I had more time. It's 2 o'clock. So so the other thing I would have said, which we'll say next time, is if your a value is negative, your spiral is going to go inward because, right, as time goes on, e to the at is going to get smaller, smaller, smaller. And what's neat here is that if a is negative, your trace and your determinant are still the same. Your trace is still 2a. It's just now it's negative. And your determinant is still a squared plus b squared. It's still positive. So big picture, and I know I said this in class already, is that if your determinant's negative, it's a saddle every time. Always a saddle if your determinant's negative. If your determinant's positive, then you have options. You might have spirals, you might have nodes. You might have stability, you might have instability. Stability is completely determined by the trace. If the trace is positive, it is unstable. If the trace is negative, it is stable. And then spiral versus not spiral completely depends on whether you end up getting a negative or a positive number in your discriminant, right? If you're thinking about like the quadratic formula, if that thing inside the square root is negative, it's going to be imaginary, which means we're going to have spirals. There's a really great picture, which he drew in class kind of on Monday, which is on the last page right before the problems in section 10.2. It's this picture here, which shows you if you're down here where the determinant is negative, you have saddles. If you're up here where the determinant is positive, you either have nodes or spirals. If the trace is positive, you have unstable nodes or spirals. If the trace is negative, you have stable nodes or spirals. And then this line here, which is where where you get the determinant equal to 1/4 the trace squared, that's the difference between either having a spiral or a node. We'll definitely talk more about that on Friday, but we're out of time. I should let you go.